In our first exercise, we are interested in which kinds of functions are concave, and we will be looking at, given a family of concave functions, how we can compose them in certain ways such that we will have concave functions again. So, let un of y within the naturals be a family of concave functions such that the un converge pointwise to a function u, and let c be a constant. Then let us consider exercise A. Show that u1 plus u2 is a concave function. Well, let us first consider what it means to be a concave function. If we look at the definition in Schmidli, he says that a function from an interval I into R is called concave if for all the points in the domain of this function, where if we choose x and z in I and we let x be different from z, and for all alpha in the interval 0, 1, we have that this is greater than equal to this, and we have that u is strictly concave if this inequality holds strictly. Well, that was an awful lot, so let's look at this graphically instead. Concave functions are what we typically would call the angry smileys or the sad smileys. So if we, for example, consider this function u and choose points x and y different from each other, then basically what this inequality says is that should we consider a point in between x and y given by a linear combination of the two, so 1 minus alpha x plus alpha, sorry, what I meant was z, if we should use this definition. Well, then evaluating u in this point, the function value of u in this point should be greater than or equal to the function value of u in x and the function value of u and z. Well, it should be greater than or equal to a linear combination of the two of these, which is here. So this is basically what this inequality says, and we will be doing a lot of drawings to show that certain functions are concave, or at least to grasp some of the intuition behind, because it's easier to understand this thing over here than this thing over here. So, given that, let us try to solve A. So show that the sum of two concave functions, u1 and u2, is again concave function. Well, what do we know? We know, by assumption, that u1 and u2 are both concave. So that means that u1 satisfies the definition of concavity and u2 satisfies the definition of concavity. And what does that mean? Well, let I be the domain of each of these ui's, and let's just assume that these functions u1, u2, u3, etc. all have the same domain. Well then, given x and z in I, where these two are different, so notice I'm actually just writing down the definition now, we know that following two inequalities hold. First and foremost, that u1 of 1 minus alpha times x plus alpha z is greater than equal to u1 greater than equal to 1 minus alpha times u1 of x plus alpha times u1 of z for all alpha in 0 to 1, and that this inequality also holds for u2. Z for all alpha in the interval 0 to 1. And now basically what we do is just sum up on both sides of the inequalities and we're done. So we have that u1 plus u2 of 1 minus alpha x plus alpha times z. Well, u1 times this is greater than equal to all of this, and u2 times this is greater than equal to all of this. So the sum of these two must be greater than or equal to 1 minus alpha times u1 of x plus 1 minus alpha times u2 of x. Can put this together in one like this, plus alpha times the sum of u1 and u2 of x. And that was A. So now you can see that we have that u1 plus u2 is a function that satisfies the definition of concavity, since we have just chosen x and z arbitrarily. And what we conclude from this is, hence, the sum of concave functions is again concave. And that's a good thing to remember, because we might use that in some later proof. Sum of concave functions is again concave. So this is a natural place to take a break, so I'll stop this video and I will do the rest of the parts of exercise 1 in the next video.